Consider the width of a single human hair. It measures roughly 0.07 millimeters across. In the world of modern manufacturing, that distance is considered quite large. We have entered an era where industrial machines operate within a tolerance of 0.01 millimeters, a scale that is nearly impossible for the human hand to maintain consistently. This level of precision is not just a feat of engineering. It is a fundamental shift in how we interact with the physical world. While we rely on our eyes and muscles to adjust to changes, these machines rely on a different kind of physics to achieve a consistency that never wavers. The journey to this level of precision began in 1961 at a General Motors plant in New Jersey. This was the home of the Unimate, the first industrial robot. It was a massive, 2-ton hydraulic arm designed to perform a task too dangerous for people, lifting red-hot pieces of die-cast metal and stacking them. The Unimate was impressive for its time, but it was clunky and relied on magnetic drum memory. It followed a sequence of steps with little awareness of its surroundings. It didn't need to be precise to the micron. It just needed to be stronger and more heat-resistant than a human. As industry progressed, the limitations of hydraulic systems became clear. Hydraulics are powerful, but fluids are messy and can compress under pressure, leading to slight inaccuracies. To reach the next level of precision, engineers turned to electric motors and a specialized type of mechanical transmission known as strain wave gearing, or harmonic drives. Unlike a traditional gearbox where teeth can have a small amount of play called backlash, a strain wave gear uses a flexible metal ring. This allows for incredibly high torque and near zero backlash, meaning when the motor stops, the arm stops exactly where it is supposed to. To understand why 0.01 millimeter precision is so difficult, we have to consider the environment. Materials expand and contract with temperature. If a factory floor warms up by just a few degrees, a 3-meter-long steel robot arm can actually grow in length by a fraction of a millimeter. To combat this, modern robots are equipped with thermal sensors and sophisticated software. They calculate their own expansion in real time and adjust their movements to compensate. The machine is essentially dreaming of a perfect, stable coordinate system while existing in a world that is constantly shifting and expanding around it. Precision is only half of the equation. The other half is speed. Some modern Delta robots, which look like 3-legged spiders suspended over a conveyor belt, can perform over 200 picks per minute. At this speed, the movement is a blur to the human eye. To keep this speed from shaking the machine apart, engineers use advanced feedback loops. Optical encoders at each joint track the position of the arm thousands of times per second. If the arm deviates by even a hair's breadth due to momentum, the controller sends a corrective burst of electricity to the motor to pull it back on track. The culmination of this technology is the lights-out factory. In these facilities, the lights are literally turned off because the workers do not have eyes. Robots don't need photons to perceive their environment. They navigate through programmed logic and internal sensors. A factory in Japan, owned by Fanuc, has been known to run for weeks at a time without human intervention. In the dark, these machines build other machines, operating with a silent, rhythmic efficiency. It is a sterile, calm environment where the variables of human fatigue and error have been removed entirely from the production floor. One of the greatest challenges in robotics is the concept of stiffness. When a 10-ton robot arm extends to its full length, the laws of physics want it to sag slightly under its own weight. To maintain sub-millimeter accuracy, the structural components are cast from high-strength aluminum or carbon fiber. The math required to move such a mass is complex. The controller must calculate the inertia of the arm and the payload at every microsecond. It isn't just moving a tool from point A to point B. It is managing a violent surge of kinetic energy and bringing it to a dead stop with surgical grace. While industrial robots excel at repetition, they have historically struggled with tasks that humans find simple, like picking up a random object from a bin. This is known as Moravec's paradox. High-level reasoning requires very little computation, but low-level sensory-motor skills require enormous computational resources. We are now bridging this gap using 3D vision systems and machine learning. By projecting laser patterns or using stereoscopic cameras, robots can now see depth. They can identify an object's orientation and calculate the best way to grip it, blending the brute force of an industrial machine with a new kind of digital spatial awareness. We are also seeing the rise of collaborative robots, or cobots. These machines are designed to work alongside humans without the need for safety cages. They use sensitive force torque sensors to detect the slightest touch. If a human arm crosses its path, the cobot feels the resistance and stops instantly. This represents a shift from robots as isolated tools to robots as partners. They handle the repetitive, high-precision tasks that cause strain in humans, while the human provides the flexibility and problem-solving skills that machines still lack. It is a division of labor based on the strengths of our respective physics. The evolution of the industrial orb is a story of knowing the gap between intended and reality. We have moved from the crude movements of the 1960s to a world where machines can manipulate the physical environment with more precision than we can perceive. As we continue to refine the gears, sensors, and algorithms that drive these machines, the limit of what we can build is no longer our own physical dexterity. Instead, the limit is our imagination. We are building a world that is more precise, more efficient, and increasingly, one that can operate with perfect accuracy even in the dark.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.